I'm Florian Beser, a postdoc researcher at the Vienna University of Technology. My research is focused in geometric analysis, in particular convex geometry, with applications to differential and stochastic geometry.
I'm Daniel Rosen, a postdoc at the Ruhr University Bochum, working mainly on symplectic and differential geometry and their intersections with stochastic geometry.
I am Christoph Taylor, Professor for Probability at Ruhr University Bochum. My main research area is stochastic geometry. The study of random polytopes, also called random convex hulls, has a long tradition in stochastic geometry with numerous applications to, for example, convex geometric analysis or optimization. The most classical model can be explained as follows. Let K be a convex body in the d-dimensional Euclidean space Rd of volume 1, x1 up to xn be independent and uniformly distributed random points in K, and denote by Kn the convex hull of these random points. The expected missed volume of Kn measures how well the mother body K is approximated by the random polytope Kn. Starting with the pioneering work of Reni and Sulanke, the asymptotic behavior of the expected missed volume was intensively studied, among others, by Barani and Schütt. If the boundary of K is sufficiently smooth, the expected missed volume decays for large n, like a dimension-dependent constant Cd times n to the minus 2 divided by d plus 1 times an integral of a power of the Gaussian curvature of K, which is well known in convex geometry as the affine surface area. Later, Reitzner has obtained matching lower and upper bounds on the variance of the volume of Kn, and he also proved asymptotic normality. From the point of view of approximation of K, a drawback of this random polytope model is that not all of the generating points x1 up to xn are vertices of Kn. This changes when random inscribed polytopes are considered. Here, the generating random points are uniformly distributed on the boundary of K. If the boundary of K is again sufficiently smooth, the expected missed volume has been investigated by Buchta, Müller-Tichy, Reitzner, Schütt, and Werner, for example. Again, this quantity decays for large n, like a dimension-dependent constant, times n to the minus 2 divided by d minus 1 this times, and another curvature integral. Also for this model, matching lower and upper bounds on the variance of the volume are known, and the central limit theorem has recently been proved.
Our work studied random polytopes in non-Euclidean geometries. The two best-known examples of such geometries are the spherical geometry in a hemisphere of the d-dimensional unit sphere and hyperbolic geometry in d-dimensional hyperbolic space. Let us point out here that both spaces carry canonical volume measures, which can be defined, for example, as the d-dimensional Hausdorff measure. In particular, this means that the uniform distribution on a convex body K is well defined. In either case, we fix a sufficiently smooth convex body K of volume 1 lying in either model space. We take x1 through xn to be independent points uniformly distributed inside K. We denote their spherical or hyperbolic convex hull by k sub s of n or k sub h of n, respectively, which gives a random polytope inside K. We study the volume of this random polytope and prove first a lower variance bound for this volume, which has the same asymptotic behavior as in the Euclidean case, namely n to the power negative d plus 3 over d plus 1. Additionally, we prove that the volume satisfies a central limit theorem. Similarly, we consider random inscribed polytopes in spherical and hyperbolic geometries, which are, as before, the convex hull of n independent points uniformly distributed on the boundary of a convex body K. Again, we prove a lower variance bound for the volume of the random inscribed polytope, which has the same asymptotics as in the Euclidean case. This time n to the power negative d plus 3 over d minus 1. Additionally, we prove that this volume satisfies a central limit theorem. Finally, let us mention that both results apply more generally to so-called projective finished geometries. Two famous examples of such geometries, apart from hyperbolic or spherical geometries, are the so-called Hilbert and Funk geometries inside the convex body in RD.
One of the main ideas in our proofs is to consider projective models for spherical and hyperbolic spaces. For example, if we consider the sphere as a hypersurface in Euclidean space, then the projective model is obtained by radially projecting an open half sphere to a tangent hyperplane. This is illustrated in this picture. This is also known as harmonic projection. A similar construction is also available for the hyperboloid model of hyperbolic space. And one thing to notice here in particular is that geodesic arcs are mapped to affine line segments. So in these projective models of spherical and hyperbolic spaces, affine line segments are geodesics, and therefore the geodesic convex hull is equal to the Euclidean convex hull. In other words, a spherical convex body is mapped uniquely to a Euclidean convex body via harmonic projection. This allows us to consider projective models for our non-Euclidean geometries. Of course, we do have to replace the Euclidean volume measure with the image measure with respect to the harmonic projection, which turns out to be a weighted volume with a continuous weight function. These considerations lead to the idea of our meta theorems, where we just consider weighted volumes of the Euclidean convex hull of non-uniformly distributed points in the Euclidean convex body. In the end, by simply plugging in the right weight functions for the image measure, we can then easily derive the spherical and hyperbolic and even more general cases. So to be more precise here and to set up our meta theorems, let us first consider a Euclidean convex body K and some bounded and continuous weight function on the convex body K. Furthermore, we consider the random points inside K to be distributed non-uniformly with respect to a bounded and continuous probability function. So under these very mild assumptions, we are able to establish our first meta theorem, which gives us a lower bound on the variance of the weighted volume of the weighted random convex hull, and we also obtain a central limit theorem. So if you pay attention to the rate here, you'll notice that it is exactly the same as in the Euclidean result for the volume of the convex hull of uniformly distributed points. And now this generalization allows us much more control. In the proof of our meta theorem, we employ different tools from geometric analysis, such as the concept of convex floating bodies and of probability theory. So also in the situation where we choose points on the boundary rather than inside the convex body, things are very similar. So here we now consider weight functions that are supported on the boundary of the convex body only. In a more recent work, we are also establishing a lower bound for the variance of the weighted volume with an even better rate of convergence, of course, and the central limit theorem. As mentioned, using these meta theorems, we are then able to treat the spherical and hyperbolic spaces just as special cases, and this leads to this more general framework of so-called projective geometries. Okay, so this brings us to the end of this short presentation. We thank you very much for your attention, and please consider looking into our articles for more precise information and much more background on the scope of our theorems. Thank you for watching.